Yeah, I was sick. Okay. Good afternoon, everyone. Well, today we are really happy to have Professor Peisi Huang from University of Nebraska, Lincoln, to give us a talk about the cosmological phase transitions. Let me give a brief introduction to Peisi. Peisi graduated from University of Wisconsin-Madison, then did her postdoc at U Chicago and Texas A&M. Then she became faculty at Nebraska, Lincoln. Now she's on her sabbatical, visiting different places. Today we're really looking forward to have Peisi giving us a talk on this. She's an expert on BSM phenomenology, in particular along Higgs physics and phase transitions. Let's go ahead.
Yeah. Thanks, Jim. Yeah, thank you very much. It's truly a great pleasure to be here. And I'm going to talk about cosmological phase transitions, and in particular, some of the interesting phenomena that could occur during those phase transitions in the early universe. So I will talk about three things. I call them the asymmetry, the dark, and the inverse. So yeah, we'll get to what they are. So let me start with the asymmetry. So one of the major motivation to study phase transition is baryogenesis. Matter-antimatter asymmetry remains one of the greatest puzzles in particle physics, and phase transition provides the right condition to address that. So let me start from that. So here is the usual story for baryogenesis. There are three conditions to be fulfilled to generate the baryon asymmetry. The first one is we need the process to generate actual baryons or baryon number violation. And then we need the process to prefer matter over antimatter or CP violation. And then we need the process to take place out of thermal equilibrium. And a first order phase transition provides the necessary condition, provides the necessary departure from thermal equilibrium. Besides baryogenesis, another interesting mechanism to generate matter-antimatter asymmetry is leptogenesis. That solves two puzzles at once. In type 1 seesaw, we introduce a right-handed neutrino with mass m. It interacts with this left-handed neutrino through the Dirac interaction. And because of this Dirac interaction, it mixes with the left-handed neutrino. After diagonalizing the mass matrix, we get the mass of the standard model neutrino that goes like 1 over capital M. So that works like a seesaw. And this exact Lagrangian satisfies all three conditions for baryogenesis. The Majorana term violates lepton number, the Dirac term violates CP, and the right-handed neutrino decay when the cosmic temperature falls below its mass provides the departure from thermal equilibrium. So in this very Lagrangian, all three Sakharov conditions are satisfied and neutrino masses are generated. So I should mention there is a vast literature on leptogenesis, including the ones from local experts, but I'm skipping them here. So there are three steps in leptogenesis. The first one is the asymmetric decay of the right-handed neutrino. At the leading order, the decay is symmetric. So the right-handed neutrino decays to lepton and anti-lepton at the same probability. At the next two leading order, we have the one-loop diagrams. They interfere with the tree-level diagram, and the interference leads to an asymmetry in the right-handed neutrino decay. And the asymmetry is proportional to lambda d Dagger square, the imaginary part of lambda d Dagger square. And then in the second part of the generated asymmetry will be converted to a baryon asymmetry through the Spiller process. So this part is pretty efficient. It's about order 1, and detailed calculation shows about 28 over 79. The major difficulty in leptogenesis is in the third step, the washout processes. So there are leptons and Higgs in the thermal baths. They can annihilate through a right-handed neutrino, And also they can scatter through a T-channel right-handed neutrino. Those processes generate anti-lepton at the cost of lepton and therefore erase the generated asymmetry. So one can show that only about 1% of the generated asymmetry survives, and I'm going to talk about how to fix this 1%. So naively, the strong washout effect is not avoidable. The final generated lepton asymmetry is a competition between the right-handed neutrino asymmetric decay and the washout processes. So the right-handed neutrino decouples from the thermal bath as the cosmic temperature falls below its mass. So the speculation I'm going to make here is, what if the cosmic temperature can change discontinuously? So let's just imagine that can happen for a second.
So, question about this difficulty. What's difficult? I mean, don't you get the asymmetry at the end of the previous slide? And you said you get 1%, but
Yeah, sure. So
but don't you get the baryon asymmetry at the end? You
Yes.
still get it.
yes, absolutely.
So
So
what's the problem?
so the problem
Trying
we're
to fix.
the problem we are trying to fix is if we can make this process more efficient, therefore one can have smaller CP violation and therefore make the model building for that part more comfortable.
I see.
Yeah.
But the standard scenario works fine up to this 1%. Right?
The standard scenario works fine in certain parameter space for this 1%.
So you're going to be able then
To extend the parameter space precisely.
Yeah.
Yeah. Thank you. Okay. So let's imagine the cosmic temperature can change discontinuously for a second. Then the story will be the following. At high temperature, the right-handed neutrinos are in thermal equilibrium. As the temperature falls down, it decouples from the thermal bath when the temperature falls below its mass. And then right-handed neutrino decays, generates the lepton asymmetry, and then suddenly the cosmic temperature changes to a temperature that is much below the mass of the right-handed neutrino. And then in that case, the washout processes are Boltzmann suppressed, so all the generated asymmetry will survive. Well, it is difficult to change the temperature discontinuously. There are two sides of this equation, the temperature, the cosmic temperature, and the mass of the right-handed neutrino. It may be difficult to change the cosmic temperature discontinuously, but the other side of the equation, the mass, can change discontinuously through a first-order phase transition. To do that, it is straightforward to do that. We just couple the right-handed neutrino to a scalar field that undergoes a strong first-order phase transition. The right-handed neutrinos are massless in the old vacuum in the white region here. And then during the phase transition, the right-handed neutrino gains mass, which is much larger compared to the phase transition temperature, for example. Then we create a discontinuous jump in the right-handed neutrino. So if the mass is much larger compared to the phase transition temperature, the washout processes are Boltzmann suppressed. In the true vacuum, the right-handed neutrino decays immediately, and the washout processes are Boltzmann suppressed. The generated asymmetry survive.
Your phi is real or complex?
It could be real. So it doesn't matter too much here.
There are no domains.
So we can make it real, we can make it complex. So it does not really matter for this kind of
If
thing.
phi is real, then I could think of
Then we have a domain for
right.
Yeah.
If it's really a double well, then you have the left and right that walk and below.
So yeah, I think we can. So we didn't go
You
into
can have
yeah.
the symmetry.
Right. Yeah.
But if it's complex, you'll have a Meyer,
Yes. Yes. You have. Yeah. Yes, you do.
and then you have to give it a mass.
Yes. Right. So in this one we didn't do that part. But I think there are follow-up work from other people who introduced the Marion. Yeah.
You're going to require a coincidence, right? Which is the phase transition temperature for this phi sector coincides with where the right-hand neutrino decays. I'll get out of equilibrium.
So
Or you can give the diamonds out of phi.
So it does not.
Then there will be a mass.
So as long as, okay, so the only thing we require is it's much lower than the mass.
You require what?
The phase transition happens much below its mass. So so we don't want it to happen there other than, so if that is the case, the washouts are still there. So we want to,
So the vet of phi is not the right, is not gonna give the mass to the right-handed neutrino.
it is.
Can see.
It contributes, but it's not the dominant mass, is it?
So here, in this case, so in this case, in the simplest case, we have the phi gives all the mass of the right-handed neutrino. Yeah. Okay. Does it sound good? Really? Does it sound good? Yeah, I'm expecting a question here.
But you requiring so what are you requiring the value is much bigger than the transition temperature.
Yeah, very good.
That's it.
Yeah.
Does that do the work? I think it will give the right-hand neutrino mass, and
Yes.
right-hand neutrino will decay symmetrically.
Yeah. Right.
And you say simultaneously with the rescattering, which washes out will stop because
They're both mass
because
suppressed.
the thermal temperatures are
Yeah. Okay. I think it's a good place for you to say, wait a minute. There is a question, right? So I'm talking about the right-handed neutrino mass to be much larger than the phase transition temperature. Then an obvious question is, energy conservation tells me if my cosmic temperature is much below the right-handed neutrino mass, there's no enough energy to create those right-handed neutrino in the true vacuum. And therefore, we really expect them to be trapped in the old vacuum. Does that make sense? Okay, so if that makes sense, then the trick in the scenario is actually the following. So we need the phase transition to be very strong, which also can be seen from the fact that the right-handed neutrino gets all its mass from the web of the scalar, and it is much larger than the phase transition temperature. So if the phase transition is very strong, then the bubbles can be ultra-relativistic. Then although if we are looking at the problem in the plasma frame, we may expect the right-handed neutrinos are in thermal equilibrium. But if we look at the problem in the wall frame, they are highly energetic in the wall frame. And therefore, they have enough energy to penetrate into the true vacuum with part of its kinetic energy converted to the rest mass. And they go to the true vacuum and then they decay immediately. So then for the model building part, what we need to do is, so we have this coupling, and we need to write down effective potential for this phi. And there are two conditions for this phi. First of all, we need the mass of the right-handed neutrino to be much larger than the phase transition temperature. And then we need the right-handed neutrino can actually penetrate into the true vacuum other than being stacked in the false vacuum. For that, we need the bubble walls for the phase transition to be ultra-relativistic. So the model building task is we need to find such a potential.
So here the right-hand neutrino decay precede cosmological phase position, right? This right-hand neutrino decay precedes the phase transition, right?
So they decay all the way, but they decouple.
The decay happens before the phase transition, right?
Yeah,
Then you have a leptogenesis symmetry, right?
Yeah.
And then after that, you have a phase transition, right?
Right.
But
What happened before?
that's what I mean. Then before phase transition, how can you have a decay? Because you don't have a mass of right-hand.
Before the decay, well, okay, so it's not a decay because, like you said, it's massless before the phase transition. So it's in thermal equilibrium before the phase transition, and after the phase transition, it goes to the true vacuum, acquires the mass, and it decays immediately. And then at that temperature,
It decays only inside the vat.
in the blue region,
inside the
bubble.
bubble. I see.
Yeah. And then in the true vacuum, since the temperature is much lower than the mass of the right-handed neutrino, the washout processes are both mass suppressed. Therefore, I don't have to worry about the washout. So that's the trick.
Wouldn't be more natural right-handed neutrinos would just undergo full reflection from the wall because it's sort of very massive on the inside. And then we very naively would like to reflect from the wall.
Yeah.
And go back to the wall.
Yeah, so that can be calculated. So I don't think I have one here, but you can calculate. So for a given mass of the so for a given mass or temperature, and then for a given wall velocity, one can calculate the penetration rate of the right-handed neutrino. So if it is 1, then the penetration rate is actually very high. So this only happens if the wall is highly ultra relativistic. So even if it is 0.99, then it falls down quickly at say 20, for example. So okay, so we need ultra relativistic bubble wall. The wall velocity is determined by the vacuum pressure and the frictional force. The vacuum pressure is from the free energy difference between the true and false vacuum. And at the leading order, the friction comes from the mass difference from different on two sides of the wall. And if the vacuum pressure is much larger than the frictional force, the wall will be accelerated to a high speed, which we want. And at that time, and when gamma W is high, then higher order correction becomes important. The next leading order calculation shows the friction is proportional to gamma W. So W here is the wall. And all order resummation remains an open question right now. So some calculation shows gamma W, some calculation shows gamma W square, and then one can calculate the terminal velocity corresponding to different resummation calculations. So then one example we can think of is we can just do simple U1 B minus L. So ultra relativistic walls can be achieved when the vacuum pressure dominates over the friction. And in for the minimal U1 B minus L, those also shows that even if MC prime is at 10 PeV, once I lower the gauge coupling, I can have percolation temperature to be as low as MeV scale. With a very low percolation temperature, this condition can be easily satisfied, and therefore I expect ultra-relativistic bubble walls from this simple case.
So in your scenario, are you gauging U1 B minus L?
Yes.
Well, then Y must be B minus L carrying, it's complex scalar, right?
So the
I think Y must be B minus L carrying complex scalar.
yes,
So that
yeah,
you have a phi right energy and right energy as a gauge in your right?
yeah.
But you said that can be real, right?
So okay, so if I don't build a real actual model, it can be real. So this is just one example. So here you're free to so you're free to write your own potential as long as it gives an ultra relativistic bubble.
So this is one example.
Yeah, this is one example.
Yeah, but if you're gauging B minus L, then it'll beat the Meyer.
That's right. The longitudinal the axion of B1 itself becomes the longitudinal part of B1 itself.
So again, here we didn't worry about the Marion. There are follow-up work. They take that into account. I don't think that results change much yet. So okay. So looks like for a minimal U1 B minus L, it has everything. It has right-handed neutrino couples to the scalar, and that scalar seems to satisfy everything we talked about. There is one thing we have not asked is we say the right-handed neutrino penetrate into the true vacuum, but we never asked what happens after the penetration. So for example, are there any competing processes and are there any additional washouts from the decay products? Because the right-handed neutrinos are highly energetic, the decay products are highly energetic. So are there problems there? And what about the stronger heating? We have strong first order phase transitions, so there are stronger heatings. So let's look at those three things. First, right after penetration, we want the right-handed neutrino to decay, but there are two competing processes. They can annihilate through a Z prime. They can scatter with the standard model particles in the plasma. So for leptogenesis, we require the decay rate to be larger than annihilation and scattering. And a second thing is, as I just mentioned, the red-handed neutrino is highly energetic. This high energy is shared by the decay products. So they can fuse back into an unshelled red-handed neutrino, leading to washout. So to avoid that, we ensure the thermalization is fast enough. So we require the thermalization is larger than this process and also Hubble. So therefore, the decay products can quickly lose their energy to the plasma to avoid this process.
What is gamma?
On shell, so that neutrino can be on shell.
Yeah.
Yeah. So those two turns out to not be a big problem. The major problem is the strong reheating. So from a very strong phase transition, we expect a large latent heat released from the phase transition that will reheat the universe. And for phase transition to provide ultra-relativistic bubble walls, typically this alpha is much larger than 1. So the reheating temperature is typically high. A high reheating temperature means the washout processes are reactive again, and they are no longer Boltzmann suppressed, although they were Boltzmann suppressed at the percolation temperature. And also, the generated asymmetry will be diluted by T phase transition over T reheating cubic. So this turns out to be the major difficulty in the minimal model. So in the minimal model, this coefficient has to be positive for spore stability, and that imposes the Z prime mass is higher than the right-handed neutrino mass. And one can show that the reheating temperature is pretty much the Z prime mass, which is larger than the right-handed neutrino mass. And that means the washout is again no longer avoidable. So to fix that, what we do is we just want to break the correlation between the reheating temperature and the right-handed neutrino mass. So to do that, we introduce a scalar that couples to the scalar field that undergoes a phase transition. So we have additional contributions from the column member potential, and therefore the reheating temperature and the mass of the right-handed neutrinos are no longer correlated, so we can avoid the washout. So
how do you estimate the reheating temperature? What are the parameters in here?
yeah, I can show you. There are some calculations involved here. Yeah, I'm just writing it this way, so it's easy to see the correlation. So then that opens up the parameter space. So here the blue region is excluded because the reheating temperature is too high, so the washout processes are reactivated. In the yellow region, the generated asymmetry is diluted too much. And in the white region, we can have successful leptogenesis. And also we can lower the required CP violation to about a factor of 30. So let's look at some signal using this point. So the signal wise,
The itself and the 40, this is 40, lambda phi s.
lambda phi is the portal.
It's very large.
Yeah, we're looking at large couplings. Okay, yeah, so let me show you some signals. So the signal from phase transitions are at pretty high frequency, so pretty difficult. But we have the cosmic strings from the U1 symmetry breaking. So that's the first scenario I want to talk about. So we can suppress the washout from leptogenesis in a first order phase transition. Does that sound good? Okay. So let me move to the second thing, which I call the dark. And in this one, I'm going to show you one example of how to enhance the dark matter abundance in a first order phase transition. So let me start with the usual story. The dark matter relic abundance is measured by WMAP and Planck to be 0.12. And then at the same time, for a given particle physics model, the dark matter relic abundance can be calculated by solving the Boltzmann equation. And at larger, so what matters from the particle physics model is the annihilation cross-section, larger annihilation cross-section, meaning smaller relic abundance as shown here. So that means for a given dark matter mass, there is a magic number for the annihilation cross-section so that it gives the right relic density. And for WIMP dark matter, that magic number is about 10 to the minus 26, which sets a target for indirect detection experiments. So in this work, the authors perform model independent analysis for dark matter indirect detection experiments. And they show the green region, which they call visible, is excluded by combining indirect detection experiments together. The purple region is excluded by unitarity bounds. And this orange line is the WIMP window, and obviously it's a narrow window, and we are talking about the the open white triangle here. So the question I want to ask is, can models with higher cross-section give the dark matter abundance?
Sorry, what is the green? Yeah. Green region?
In indirect detection? So the
indirect detection excluded.
Excluded, yeah.
Assuming they are full dark matter. So you don't ask what's the, well.
That's not, precisely. So to answer this question, let's look at the Boltzmann equation. So the Boltzmann equation is a first order equation, a differential equation. It requires one boundary condition to solve. And for the standard thermal freeze-out picture, the boundary condition is that early on, before the freeze-out, the dark matter number density traces its equilibrium number density. So to change the solution to the Boltzmann equation, we can change the boundary condition. So in this plot, all three lines have the same annihilation cross-section, but they have different boundary conditions. So they have different, so we have different solutions to the relic abundance. So the basic idea here is we want to save the underabundant dark matter models by modifying the boundary conditions. So we have the dark matter produced later through some non-thermal processes after the freeze-out. So this idea has been explored in the literature, including from local experts. So this is often referred in the literature as the delayed production of dark matter. So early on, the dark matter does not exist, but they are being produced from the decay of some heavy particles later on, for example, from inflatons or moduli fields. And what we are proposing here is we want to produce the massive dark matter during a first order phase transition. So what we do is we couple the fermionic dark matter field, we call that chi, to a scalar field phi through a Yukawa interaction. And then we let this phi undergoes a strong first order phase transition. So again, so here I'm not going to specify the underlying particle physics model for the phase transition. So to keep the discussion more model independent. So if you have a favorite model, you feel free to put it there. So this chi is massless before the phase transition and acquires a mass of m after the phase transition. And then in this way, we produce the massive dark matter during the first order phase transition. So we can do a quick estimation for the relic abundance. So since the dark matter is being produced after the freeze-out, so we can ignore the equilibrium term. So what matters here are the competition between the expansion and annihilation. So to trace that, we define a critical number density by equating the expansion and annihilation rate. And let's consider two scenarios. The first one is shown in this yellow line, in which the number density at the production, which in our case is the phase transition, is lower than the critical number density. And in that case, the expansion dominates over annihilation, and the relic abundance is already frozen at the time of the production, so it's not a very interesting scenario. A more interesting scenario is this blue line, in which the number density at production is higher than the critical number density. The annihilation dominates the cosmic expansion here. So we expect rapid annihilation until the two rates are equal, and the dark matter density begins to stabilize, and the final abundance is enhanced by a factor of T result over T phase transition. So here, by doing that, we can open up the parameter space. For the thermal models that predicts underabundant dark matter, we can fix them by having a delayed dark matter production. And then for a given annihilation cross-section, one can calculate the corresponding production temperature, which we call T production or T phase transition in our case, color-coded in this plot for an enhanced dark matter abundance to match the observed value. And typically we find M over T to be in the region of 100 to 10 to the power 4. With that, we can discuss some signal. So we have a strong first order phase transition. So we expect gravitational wave backgrounds from first order phase transition. The gravitational wave signal is determined by 4 parameters: alpha, the strength of the phase transition; beta or H, the duration, the inverse duration of the phase transition; temperature of the phase transition; and the wall velocity. So the strength of the phase transition is proportional to alpha over 1 plus alpha squared. And typically we see M over T is at least 100. That implies very strong phase transition. So alpha is much larger than 1, and therefore that saturates this ratio here. And phase transition temperature is determined by the mass and annihilation cross-section, so from this plot right here. And then the wall velocity is determined by requiring enough dark matter is produced at the phase transition temperature. So we want to make sure we're in the blue region, not the yellow one. So from some calculation like this. So after doing those steps, we only have one free parameter left. So we only have this beta or H. So of course, when you specify your particle physics model for the phase transition, all parameters can be calculated. So here again, we try to keep the discussion more model independent. So now we have one free parameter here. So in this plot, what we do is we take the points from the open triangle in the dark matter parameter space, and then we calculate the peak frequency and the strength at the peak frequency. And we see that the gravitational wave signal peaks are well within the proposed and upcoming detectors' sensitivities. So here we have 4 islands, different islands correspond to different beta over H values. So for small beta over H, we have the pulsar timing arrays that can probe those signals. For beta over H around 100, the most promising one will be LISA. And when beta over H is about 10 to the power 4, that moves to BBO and Disigo region. And again, we have the dark matter indirect detection experiments. So here we also put the upper bound from tau annihilation. So how is here, and we have lasso S, and also we have this projected sensitivity also from tau plus tau minus from CPA.
Sorry,
Yeah.
the regions are all excluded. Things like has and lasso all exclude everything above. Right?
Yeah.
So what are the surviving regions?
Okay, so in this region, so that's a model independent combination. So that's also part of the reason it is in
Yeah, the pink region already excluded, right? By indirect.
is in this region.
Right.
So when you do like a given annihilation channel, it becomes a little bit more the model dependent question. So yeah, so that's the reason I want to show both here. So if you want to do a model independent analysis, then obviously you have much weaker bound. So that's this one. Yeah. Okay, so indirect detection and gravitational wave together provide a powerful multi-messenger probe for this scenario. the disk here are the points that are compatible with Hess, and the crosses are the points that will be excluded by Hess from tau plus tau minus. But all points here are from this open triangle. So if you do a model independent analysis, all those are still there. And the points that I do black outlines are the points that will be within the CTA sensitivity. The colored bands shows the sensitivity range for some gravitational wave interferometer. And let me remind you, the gravitational wave signal peaks are well within the proposed detector's sensitivity. So this plot shows a nice complementarity between gravitational wave interferometers and dark matter indirect detection experiments. Gravitational wave probe the dynamics of the phase transition, and indirect detection constrain the annihilation of dark matter. So that's the second story I want to tell you. So I want to show you that the dark matter property can be different from what we naively expected if there was a first order phase transition early in the universe. And the last one, so it's Friday afternoon, so I want to entertain you a little bit. I'm going to talk about something called the inverse. And in this part, I'm going to constrain myself to electroweak symmetry for most of the time and ask the question, can electroweak symmetry be restored during a first order phase transition instead of being broken? So again, let me start with the usual story. So the usual story we discuss about electroweak phase transition is the following. So we say at high temperature, the universe is in the symmetric phase. The Higgs has a 0 vacuum expectation value. And as the universe cools down, electroweak symmetry is broken, and the Higgs acquires a non-zero vacuum expectation value. So this is the normal picture we talk about. However, on this whole slide, the only thing that is true is this one. So we know the Higgs today has a non-zero vacuum expectation value because we have measured that. For the Higgs lab at high temperature, we don't have any probe. And also, we don't know what happens as the universe cools down. We don't know if even this is true. We don't know if it is as simple as a symmetry breaking process, or it can be more complicated thermal history of the universe. So those questions are not crazy to ask. So in 1974, Wimberg has shown that gauge and global symmetries can be non-restored at high temperature. And symmetry non-restoration or inverse symmetry breaking has been realized in nature. And one example is the washout salt system at minus 18 degrees Celsius. When you lower the temperature, the symmetry is actually being restored other than broken. So the question, so I'm going to ask the same question for the early universe. Is that possible that as in the early universe, as the universe cools down, electroweak symmetry is restored instead of broken? So is this possible? So when we lower the temperature, the vacuum expectation value goes from non-zero to 0. So that I call inverse symmetry breaking. And so a while ago, Jane asked a similar question. Is it possible that electroweak symmetry is never restored even in the early universe, which is called symmetry non-restoration? So to discuss that, let me first write down a condition for electroweak symmetry non-restoration. So
can I go back to your left plot? So you want to restore symmetry again, then break again at a higher temperature, then restore it again. It's from your plot.
Yeah.
Why do you want such complex behavior? Well, fun.
Yeah, just for fun, I guess.
Because you don't need to start with the 0 at high temperature.
Yeah, you don't need the last.
You don't need the last bit.
Right, you don't. So there are two reasons I do this. One is in the model I'm about to show you, we cannot have this, so it has to restore that high temperature. And another reason for I find this to be interesting is, so recall in the discussion for by leptogenesis picture, the major thing is, so we want the bubble wall to be highly relativistic, and the major difficulty there is the phase transition has to be very strong, reheating temperature is high. But here, if we can have inverse symmetry breaking, then we have acceleration of the wall from the vacuum pressure, and also we have the friction we talk about in phase transition like this becomes an acceleration in phase transition like this. So that's the reason I'm more interested in a phase transition like that. And there can be other implications. So that's the, yeah, and mostly for fun, of course.
The symmetry restoration, what happens to topological defects? Imagine all your, it might be possible to have a Boston string. But then what happens, sorry, but just for my curiosity, what happens?
That's a good question. Yeah, we can think about that. Yeah.
Will you explain?
Yeah, I don't have a clear picture for that right now, but yeah, I could imagine some of them.
Wouldn't this effect will relax, because the topological numbers will after quantity?
Yeah.
So that's a number question, right? So some of them will be, yeah.
That is zero, so.
So symmetry is broken again. Yeah. Yeah. Yeah, that's a good question. Yeah. Yeah, I think that's good. Yeah, I think that's something interesting to explore for sure. Okay. Yeah, so before I tell you the story, so let's first write down the condition for electroweak symmetry non-restoration. So the standard model scalar potential at zero temperature looks like this. So that has a spontaneous symmetry breaking. And then the leading one loop thermal corrections of the Higgs potential are given by the JB and JF functions for one bosonic degrees of freedom and one Dirac fermionic degree of freedom here. So at high temperature, those contributions goes like T to the power fourth, and even the leading order goes like T squared. So at high temperature, the effective potential is dominated by the thermal correction. So if we talk about high temperature behavior, we can not worry about the standard model contribution and take the second derivative of the thermal part and evaluate that at zero and take that to be the condition for electroweak symmetry non-restoration. Of course, that's a somewhat stronger condition because it is always possible there is another local minimum, just that one is not the global minimum. But let me take this let me take this somewhat stronger condition for the discussion. So from that, it's straightforward to see in the standard model, electroweak symmetry is restored. So here I expand the thermal corrections and keep the leading order contribution, and that goes like m squared t squared. So we can calculate the second derivative of the thermal part in the standard model. So we sum over all the contributions, all the degrees of freedom in the plasma. So each term here is positive. So this whole thing is positive. Therefore, in the standard model, the electroweak symmetry is restored, and we need negative contribution to achieve electroweak symmetry non-restoration. So a simple example is we just add a negative contribution, a negative portal coupling here. So then we have a negative contribution, and that leads to symmetry non-restoration. So one thing you may not like about this picture is they require a large number of singlet fields for electroweak symmetry non-restoration. So typically it's around a few hundred singlet field. So so we don't like that many singlet scalar field. So what Jen did with collaborators is that they consider inert to Higgs doubling model. There, the inert Higgs acquires a non-zero value up to very high temperature. And the good thing about an inert singlet is you don't have to pay the price of a large Yukawa as we did for the standard model. Therefore, they can reduce the number of singlet fields. So Another-
It reduces it down to 250.
Is
Is that
So
what that?
at tree level, actually reduced up to
So-
10, but we need the higher order corrections and resolution to ensure the
Oh, yes, yeah.
potential is valid up to high scale. with
Yeah,
all those
yes,
effects.
yes.
That stabilizes things.
right.
And
So-
larger than that. But
Yeah.
that's all from our higher standard of resolution.
Yeah, right, so, right, yeah, good point. So, yeah, so I think this one, they do a tree level analysis and they need a few hundred. Yeah,
So if I do the same level analysis,
Yeah.
I just need a few.
yeah,
But we want our potential to be, our stories to hold up upon some reservation, the running effect of those things. Then to make things under perfect control, when to reduce the per generation couplings as an initial value, that in large number of applications.
Yeah.
But that's because we have higher standard.
yeah, so, another way to have a negative sign is we can introduce a double H. And then when we diagonalize the mass matrix, we have a negative sign in the field dependent mass. So in this work, we try to do that. We introduce vector-like leptons, and to avoid a large mixing between the vector-like lepton and the standard model-like lepton, we so in addition to the singlet, in addition to the doublet, we need to introduce another singlet. And then in order to avoid large contribution to the T parameter, we introduce another singlet. So we have a Lagrangian that look like this. So we have two, after diagonalize the mass matrix, we have two neutral and two charged vector-like leptons. So then we can do a back of envelope calculation. So here I write down the field-dependent mass of those new fermions. And we have a minus sign that we want for the lighter state. And we have a, however, that contribution will be canceled by the plus sign, which is from the higher states. So what we expect is at very high temperature, when everything are there, the symmetry, electroweak symmetry is restored at high temperature. And then as the universe cools down, the heavier state decoupled, then we can have things driven by the lighter state, and we can have symmetry non-restoration. And then when the temperature even goes down, even the lighter state becomes decoupled. So we go back to the standard model story. At high temperature, symmetry is restored. At low temperature, symmetry is broken. And then in this process, we can have the inverse symmetry breaking that we're after. So let me show you the thermal evolution from that effective potential. So at early universe, it is symmetric. And as the universe cools down, it undergoes a crossover. Electroweak symmetry is broken. So this part is mostly driven by the thermal piece. The heavier state favor the symmetric phase, and the lighter state favor the broken phase. And the transition occurs when the contribution from the lighter state dominate over others. And then as the universe further cools down, the broken minimum becomes less deep, and a potential barrier starts to develop between the symmetric phase and the broken phase. And then at a certain temperature, we have a strong first order phase transition. The universe tunnels back to the symmetric phase. So in this case, in this step, electroweak symmetry is restored. So we have the inverse electroweak symmetry breaking that we want. So this one is driven by both finite temperature and zero temperature contributions. So they are comparable at this temperature. The standard model thermal part and zero temperature vector-like lepton contributions push toward restoring the symmetry, and like the lighter state, the thermal piece of the lighter state and the standard model zero temperature piece favor the broken phase. So the net result is a barrier between the two, making the symmetry restoring transition strongly first order. And then the universe continues to cool. The broken minimum becomes a local minimum and eventually disappears. At an even lower temperature, this trend reverses. We go back to the usual story for electroweak symmetry breaking. we have a broken minimum to form again, and eventually become degenerate with the symmetric one. So electroweak symmetry is again triggered, and this time through a strong first order phase transition. So this is again an interplay between the zero and finite temperature effects. So we have the competition between the standard model thermal contribution and zero temperature vector like lepton contribution. They favor the symmetric phase, and the zero temperature standard model piece favors electroweak symmetry breaking. So the competition generates a barrier, and that leads to a strong first order phase transition, and electroweak symmetry is broken again. So putting things together, at early universe, we're in the symmetric phase, electroweak symmetry is broken, and then restored again, and then broken again by another first order phase transition. So the interesting thing here is we only have one scalar field, but we can have multiple, we have two peaks in the gravitational waves. So the first, the symmetry breaking one is about in the range for the Disigo and BBO. And the symmetry restoring one is a little bit weaker. So when we do this plot, the projected sensitivity for BBO is about 10 to the minus 15, so you cannot really see it. So now they are claiming they can go all the way to 10 to the minus 17, even 18. So if I take that projection, then both are within the range of BBO and Disigo. So I think that's something interesting from the signature point of view. But obviously for this kind of model, we have new fermions coupled to the Higgs. So we expect strong deviations in the Higgs to diphoton rate. And indeed, we expect about 15% enhancement from the diphoton signal. And currently, the central value for diphoton rate is about 1.1, so a little bit below this. And the current upper limit is about 1.24. So yeah, so I should cut off those ones. But
It's Peisi Huang.
the phase transition strengths. But for this scenario, it will be fully tested at high luminosity LHC. So I think electroweak symmetry non-restoration and inverse symmetry breaking can be fun. They could also be important. So for example, for electroweak symmetry non-restoration, that implies baryogenesis happens at a much higher scale. So that's easier for model building, as Jen discussed a few years ago. And yeah, this is what I just said. So this could imprint. So of course here I'm not talking about electroweak symmetry breaking, electroweak inverse symmetry breaking. Then I avoid the problems for my leptogenesis story. So that also can make the leptogenesis story I just told you much easier. So that's everything I want to say. So yeah, I just show you some hopefully fun example what the phase transition can do in the early universe, and what phenomena we can expect, what signal we can expect from those phase transitions. And with that, I'll take questions.
Any further questions for Peisi? So I have a few, but let me ask one thing first. For your second part of your discussion, the reason you want to discuss dark matter production during phase transition is because you want to make into a different annihilation cross-section regime to motivate the experimental searches for that. Right? Yeah,
to show what you naively expect to be underabundant may not be. So I think that's what we want to show here.
Yeah, but the typical unitarity breaking region is still not accessible, right? So you still say, oh, if so long as I want the thermal-ish dark matter, even though they are phase transition produced, they are still in the WIMP regime. There's no expansion of that.
Yeah.
But also dark matter mass in principle can have different regions. Phase transition do not help with other mass radiance?
Yeah, right, so, it could be, so, yeah, I hope I can tell you more, but, something we're looking at is, what if in the region that we naively expect a freeze in, that can also actually gives, what happens is actually in the early universe, this is actually still a freeze out. So I think this kind of work, what we want to, the major motivation is, the dark matter property, especially, for example, the abundance may not be what you expected from the zero temperature observations.
And for your leptogenesis application, for the symmetry breaking, you still add a whole bunch of vector line.
Yeah. We may have too many vector like fermions in that case, yeah. Yeah.
Is that a lot?
So yeah, so for the current scenario we are looking at right now, I think it's going to work. We need two generations of vector like fermion.
And that's going to be up at the intermediate scale.
So we have two generations of fermions, one doing the phase transition. So they are at lower scale to just do the phase transition. The one that's doing leptogenesis, that calculation is still going on, but it's probably still in the region of 10 to the power, at least 10 to the power 9. Well, I think he has his mind, very long.
So for the first part, you had mentioned that strong first order phase period into reheating, but I noticed you didn't mention that during the second part. So if there is a strong enough phase transition for part 2, you can get an increase in the temperature of the bath.
Yeah, very good. So yeah, okay, very good. So for the second part, the one I call production is actually the reheating temperature. So for the second part, we didn't specify the phase transition model, so we just need a scale as a boundary condition.
That's really interesting. So for the first part, may I ask first, do you have a cosmic string formation? And second, if so, then how does that compare to the normal Kibble-During mechanism?
I think it should. We didn't. Yeah. So for sorry, you mean the leptogenesis part, right?
It doesn't have to be leptogenesis, but this question is more about your setup where you have a first order phase solution.
So you're worried about the domain wall problem.
I'm not worried about domain wall problem, but I'm just wondering how cosmic string forms, if it forms. I think this is different from Kibble-During mechanism, but
it could be it could be that one, right? What's the why it cannot be?
Because inside Hubble, you have many bubbles, and bubbles are growing, right?
Yeah.
So this is different from Kibble-During mechanism. Kibble-During mechanism, you have many Hubble patches.
Yeah.
Characterized like they all have the same bed, but they're characterized by different phase of the complex skeleton. And then and then at the junction you start to have a cosmic string formation because you have winding, right? Here within a single Hubble patch, you have growing many bubbles. So I just wonder if you have a cosmic string formation because you're showing gravitational wave spectrum coming from cosmic string network. So I was wondering if you have a cosmic string formation, and then how does that happen? How can I visualize that formation?
So yeah, so I think it's so for this we need the phase transition to be super cooled. So at any given time there are not that many in the same Hubble patch. So you still have the typical story for the topological defects. So that's how so at least that's where the naive estimation that I show here comes from.
And so in this case, you end up with many cosmic string within a Hubble patch, which is different from the usual case. I think normally you have a single cosmic string, normal, or order one cosmic string within a Hubble patch. But in this case, because you have many bubbles, then at every junction you will.
So in this case, we don't have that many as naively expected because it has to happen in the scenario where the phase transition is super cold. So that means in a single Hubble patch, you don't normally expect one. So you may not even have one. So, for example, I think the mean bubble separation can be that number can be very large. So that's,
Okay, great. Okay, if no further questions, let's thank Peisi again. We'll be here for the rest of the day at the PPI research office. Please stop by and check with Peisi about any physics. And also, if you want to join dinner for today, just let me know. I will send a message on Slack, or you can also email me. Okay. We aim to leave at 5:30. Okay, great.
yeah,
Thanks.
thank you all very much.
So the graduate in the first part is from bubble law
No,
collisions.